So this was a long lecture with quite some information in it, and the math could have been quite complicated at places, but I hope you at least got the main ideas and the intuition conveyed through the pictures. So we started off the class by talking about hyperplanes and the concept of linearly separable data and how I can find separating hyperplanes using this data. Now, based on this idea, we saw that one kind of potential classifier we can get from there is the one, the maximum margin classifier, which splits the data into two halves, such that the margin between the two data points is kind of widest, or the margin around the decision boundary. Now, this classifier is linear, and it was only possible to find it for separable data. Now, to deal with this issue, and particularly the case that most practical examples do not have separable data, I introduced the support vector classifier. This one was one which allowed us some slack to violate those relationships that the data has to be separable. Some points could be on the wrong side of the decision boundary or on the wrong side of the margin, and I could now still find a linear model, but the data does not have to be linear separable anymore. Now, in the last bit, we talked about support vector machines, which was a nonlinear extension of the support vector classifier. The basic idea in a nutshell being that I map my original space to a higher dimensional space, where now I can find a linear classifier, and then I map this linear classifier, the linear decision boundary, back into my lower dimensional space, in which it will be generally non-linear. And kind of the way how I'm doing it is by using things which are called kernels, and the kernels effectively define the mapping into the higher dimensional space. We saw that I do not have to do this mapping explicitly, it's done implicitly through the kernel. All I have to do is to understand those kernels, and we already saw that some commonly ones are the linear kernel, which is just the support vector classifier. Then there was the kind of polynomial kernel, where the most common one would be the quadratic kernel. And there was the radial or the exponential kernel, which is probably the most commonly one used. And there I had another little hyperparameter, sigma, the width of this kernel, which I can use to kind of choose the flexibility of my model. So I hope this gives you some good idea of how those models work, and it will help you when actually implementing those in Python and getting your hands dirty in the tutorials.